Hey everyone, hope you're doing great. If you have used Snowflake, you already know it's fast. But have you ever wondered why it's fast? In this video, I'll break down Snowflake's storage layer using a real table and the query profile, and then connect everything to micro-partitions from the official documentation. Before we start, let's quickly look at the architecture. This is from Snowflake's official documentation. We can see three different layers in the architecture. Think of this like a burger. Storage at the bottom, compute in the middle, and cloud services on the top. I'll explain the other layers in later videos. Today we are starting with the base. So the storage layer is where your actual data lives. Tables, rows, columns, files, everything is stored here. Snowflake stores this data in cloud object storage like AWS S3 or Azure Blob, but in a very optimized columnar layout. On top of that, Snowflake also compresses data automatically. Basically, Snowflake is very good at packing bags for travel. Everything fits nicely with no wasted space. For example, if a column has many repeated values like country names or dates, Snowflake can store them very efficiently in a compressed form. This reduces storage cost and, more importantly, it reduces how much data Snowflake needs to read from disk during queries. Snowflake also divides data into small units called micro-partitions. We'll understand about the micro-partitions in a bit. I created a database called Analytics Demo DB and a table called orders_demo. This is our demo dataset for understanding Snowflake storage. So this insert query right here, this generates the sample data automatically. For each row, Snowflake generates a unique order ID using a sequence function. It creates random customer ID between 100 and 1000. Then it assigns a country based on a repeating pattern: USA, India, UK, Canada, and Australia. So yes, my demo data is already more well traveled than most of us. For the order date, it randomly distributes data across the year 2023. Finally, it generates a random amount between 50 and 500. And this entire select statement is used to insert 100,000 rows into the table. We can look at the count. We can run the query here and we can look at the count. So it shows 100,000 records are present. And this query right here is calculating the total sales amount from the orders demo table. It scans the amount column and adds up all the values into a single result. I'm going to run this query now. The result gives me the total value. But what's more interesting is how Snowflake executed this query. I'll now open the query details to see what Snowflake actually did behind the scenes. It's like checking the kitchen after the food arrives. The query profile shows the actual execution plan, how data was scanned, how aggregation happened, and how much data Snowflake read from storage. This step here is the table scan. This is where Snowflake reads data from storage. This is the part where columnar storage, compression, and micro-partitions matter. On the right side, we can see detailed execution statistics for this query. So before we go and understand about the statistics, let's check what is the actual table size. I'm running this query to check the table size. So the total size of this table is approximately around 0.6 MB, which is less than 1 MB. That's very small. So because of this low data volume, Snowflake has created only one micro-partition for this table. In general, Snowflake micro-partitions typically range from 50 to 500 MB in compressed size. Since my table is much smaller than that, everything fits into a single micro-partition. So Snowflake didn't even need to break a sweat here. And here we can see how much data Snowflake actually scanned. This small size is not accidental. It's because the Snowflake uses compression along with columnar storage. Columnar storage and compression work together. Because similar values are stored in columns, they compress extremely well. This is why Snowflake can scan less data and run analytics faster. And if you look at the partitions scanned and partitions total, these two numbers tells us how many micro-partitions Snowflake read. Right now it says 1 out of 1, which means Snowflake had to scan everything because there is only one partition. With larger tables, this is where pruning becomes visible. Snowflake can skip entire micro-partitions using metadata. I'll explain partitions in a bit. If you scroll down, you can see here the number of columns used. It says 1 out of 5 columns were used. That proves Snowflake does not read full rows. It reads only the required columns. And the other important thing is the cache behavior. It says 0.0%, which means it did not read anything from cache at this point of time. But then when I try to rerun the query, it would read the data from the cache. Let me try to rerun the query. And now I'll open the query profile again. And notice it says 100% scanned from cache. That means Snowflake did not go back to the storage at all. It simply reused the previous result. This is called result caching. Basically, Snowflake saying, relax, I remember this. So let's go to the micro partitions page. So this page is again from Snowflake's official documentation, and it explains how Snowflake organizes data internally using something called micro partitions. In Snowflake, data is not stored as one big file. Instead, it automatically divided into small chunks called micro-partitions. Each micro-partition stores a subset of rows from the table. And Snowflake manages this completely automatically. We don't create them, we don't size them. Snowflake does everything behind the scenes. Each micro-partition contains two things: the actual compressed columnar data and metadata about the data. This metadata includes information like min value for each column, max value for each column, number of rows, and other statistics. This metadata is extremely important because Snowflake uses it to make smart decisions. Before Snowflake reads any real data, it first checks the metadata. If Snowflake can tell from metadata that a partition does not contain the values I'm looking for, it skips that partition completely. This skipping behavior is called pruning. One analogy. Think of micro-partitions like labeled boxes in a warehouse. If the label says 2019 data and you're looking for 2023, you don't open that box. And if you scroll down, this diagram here shows a table made up of 5 micro-partitions. Each of these blocks represent one micro-partition, and the letters from A to Z represent the range of values inside each partition, like date, IDs, or any columns you might filter on. At the top, you notice that each micro-partition contains values from A to Z. Everything overlaps. This is the worst case scenario for pruning because if I search for a value like M, Snowflake has no choice but to scan every single partition since all of them might contain M. Snowflake is basically saying, why did you organize your closet like this? As we move down, the overlap between micro partitions starts to reduce. Now each partition covers a smaller and more specific range of values. This is better because Snowflake can start skipping some partitions. At the bottom, there is no overlap at all. Each micro partition contains a unique range of values. In this case, Snowflake can jump directly to the exact partitions it needs and skip everything else. This is the best case scenario for pruning. This idea of how much partitions overlap is measured using something called clustering depth. High overlap means high clustering depth. This is bad for pruning. And low overlap means low clustering depth. This is good for pruning. So, to summarize the Snowflake storage layer, Snowflake stores data in a columnar format, which means it reads only what it needs. It compresses data, which reduces both storage cost and I/O. It organizes data into micropartitions, which are automatically managed. And it uses metadata to prune unnecessary data before scanning. All of these together makes Snowflake extremely fast and efficient for analytics. And that's not marketing, that's engineering. In the next video, I'll explain the compute layer, how Snowflake executes queries using virtual warehouses, and how it scales instantly based on workload. Thank you.